Okay, for this problem, as these giant letters across the top reflect, it's all about deciding, are we going to be using circumcenter or in-center? So first, there was the key fact that you were supposed to memorize. For each of these, by now, you should have memorized the special properties. I'll give you a hint. One of them has the special property that it's equidistant from the sides. One of them has the special property that it's equidistant. See, Tony's not. One of them has the special property that's equidistant from the vertices. Raise your hand if you know which is which right now. Raise your hand if you know which one is equidistant from the vertices, say. Okay, put your hands down. Hopefully you'll turn out to be right. Okay? You know what? Go ahead and tell me. Circumcenter, is that sides or vertices? Vertices. Most of you said vertices.
That's correct.
Okay? The circumcenter is equidistant from the vertices. The in-center is equidistant from the sides. If you did not already know that, Jacob, that's one, quiet move. If you did not already know that, these are the things that we have to study. Later I'll show you some flashcards that I made for you, some virtual flashcards. They've been posted on Edmodo. So as you hopefully study some over the weekend, use those flashcards to practice your straight vocabulary. Okay, so I'll answer that question later. So it's all about deciding, depending on the sentence that I'm asking you right now. If I'm asking you for the vertices, then you're going to say circumcenter, because that's the one that's equally distant from the vertices. If I'm asking you about what turns out to be the sides, then you're going to say in-center. So, looking at problem number 1. A developer wants to build a new hospital with service to Busy Town, Lazy Town, and Crazy Town. So you're supposed to imagine, these are the towns. So here's Busy Town, here's Lazy Town. I didn't make this up. Here's Crazy Town. And what are these lines in between the towns supposed to be? Highways. These are highways. This is I-310, like highway, Interstate 310. All of these are highways. So if the developer wants the hospital to be equidistant from each main highway, should he use circumcenter or in-center? Hold up one finger if you put circumcenter, and hold up 2 fingers for in-center on problem number 1. Okay, put them down. Most people said in-center, which is correct. Because, again, the special property, and this is just memorization, the special property of in-center is equally distant to the sides. The sides. And here, which word in problem number 1 is telling you that we want the sides? Well, equidistant could be either one. Right, the key word that tells us that we want the sides is the word highway. Because in this picture, the highways are these lines in between the cities. Highway, highway, highway. Alright, so equidistant from the highways means equidistant from the sides. That's your in-center. John. Okay, obviously number 2 is going to wind up being the other one. Okay, but let's look and see why. If the developer wants the hospital to be equidistant from each town, should he use the circumcenter or in-center? Okay, sure, obviously this one's going to turn out to be circumcenter. But tell me why. What's the key word in this sentence that lets me know? Matt, talk to me.
Well, it's from the town.
From the word town.
And they're on the vertices.
Yes.
So the answer is circumcenter.
This is what I'm talking about, okay? So, yeah, you guys, because it said we wanted the towns, and if you look, the towns are the vertices. So we'd want, in this case, we want equidistant to the towns, means equidistant to the vertices. That's circumcenter, so that's why it's going to be circumcenter this time. All right, do you guys feel like you understand number 1 and 2 now?
Yeah. Yep.
All right. This, of course, this whole lesson is going to be on Edmodo. So if anything happens just a bit too fast, that's one of the reasons why I post the video, because you can just relax and know you can always go home and just watch it again, pick up anything you missed. Okay? All right, so number 3. Number 3 gives us in-center. They just give it to us. This is the in-center. So your brain has to go, okay, in-center. All right. What are the special properties of in-center? We just reviewed it, so tell me, what's the special property of in-center? I hear sides. Okay, it's all about equally distant from the sides. So the first thing I would do if I were you working this problem is I would take my pencil or pen and I would highlight the distances that should be the same for this problem. So if it's equidistant from the sides because of in-center, then that means TY, TW, and TR. Those things I just colored in yellow, those are the things that should be the same for this particular problem. Okay? Because of in-center. Then, let's go ahead and put in the things that they gave us. So TU is 5. So here's TU being 5. And RU is 4. So here's RU being 4. Okay? So if we're supposed to find TR, which is now shown in black right now. Go ahead. Somebody raise your hand real quick and tell me, how, Ashton, how could I go about finding TR? Pythagorean Theorem. Half of the problems, if they're not just look at it and know the answer, half of them are probably Pythagorean Theorem. When in doubt, ask yourself if it's Pythagorean Theorem. Okay? So thinking of it as Pythagorean Theorem, you know, here's my right triangle happening right here. So I'm going to call this x. So it would be like this. We're talking about x squared plus 4 squared equals 5 squared. So x squared plus 16 equals 25. Whoops.
So like whenever you like do a problem, just think of square.
Anytime you do the Pythagorean theorem, it's always leg squared plus leg squared equals hypotenuse squared. So that's going to give us x squared equals 9. So x equals 3. So our x was TR. So we'll go ahead and put 3 for TR. Okay, and then Ariana is saying, look guys, look at all those yellow lines that Mr. Burton just marked. The point of the yellow lines was right at the beginning. It's in center, that's equidistant from the sides. Yellow, 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 those are all the same. So if you have one of them, you have them all. TR turned out to be 3. TY, TW, they are the other yellow lines, so they are also 3. Okay, so everybody that kind of had that blank or wrong, do you now feel like you understand it? Especially Chloe, because you weren't here the last couple of days. Did you follow that? Okay, we're good? Okay. Let's see if Pythagorean theorem happens on number 4. I don't remember if we need it or not. Okay. Now looking at number 4, perpendicular bisectors. That's weird. I was really waiting for the problem to either say circumcenter or in-center or centroid or something. But instead they're giving me lines, perpendicular bisector. This is an indirect way of still giving me one of those 4 triangle centers. Which one of the 4 triangle centers is the intersection of perpendicular bisectors? So yeah, the answer was, so for perpendicular bisectors, which triangle center am I talking about? All right, we got up to like 4 of you. That's an improvement. Circumcenter. If you see perpendicular bisector, your brain has to go, oh, circumcenter. And then your brain has to go, oh wait, special property of a circumcenter. What's that?
Equidistant from vertices.
Equidistant from vertices. It's like syllogism almost. Okay? If it's perpendicular bisectors, then it's circumcenter. If it's circumcenter, then it's equidistant from the vertices. Therefore, it's equidistant from the vertices. So let's highlight. Everybody on your paper, I'm going to do it in yellow. Color in the three parts that should be equal for this problem number 4. Okay? I better do it in blue. Okay? Okay, so for me, I've shown it here in blue. Because of circumcenter, these blue lines are the three that should be congruent. All three of those are the same. If I find one of them, I found them all. Let's go ahead and mark the things that were given. CF is 8. So here's CF being 8. BG is 12. So here's BG being 12. Okay? So now we're being asked, what is BC? Okay, so I'm hoping when you're asked for BC, you're going, oh, well, that's going to be easy. Because here's BC is right here, from here to here. Your common sense tells you that that's going to be what?
16.
That's going to be 16. Why? Yeah, you see FC is 8, and you see it's a midpoint situation, so 8 and 8 is 16. So, okay, so far, no Pythagorean Theorem. So far, so good. What about GC? And here's G right here. GC, I'm hearing you say that GC is going to just be 12. How did you know that without the Pythagorean Theorem?
Because BG is 12.
Ah, it's one of the blue ones.
You know what I'm saying?
BG was 12 already. So all of the blue ones had to be 12, including GC. What about GA then?
It's got to be 12.
GA will also be 12 for the same reason. All right, now that you see it, is it making sense?
Yes.
Am I losing anybody? Tony, how are you feeling about it? Did you understand? Okay. Okay, I'm hoping that it's going to be pretty clear what I mean when I say circumcenter. Intersection of what? Each one of these triangle centers is the intersection of some sort of a line segment. In the case of circumcenter, has anybody retained what are the little lines that meet to form a circumcenter? Perpendicular bisector. Okay, so have that memorized by Tuesday, but we'll write it down for now. Perpendicular bisectors. All right, that's what I mean by that. I'll come back to the in, out, on thing at the end. Okay, now define key word. Watch how these things all sort of link together. The key word, I'm talking about the one that we just wrote down, perpendicular bisectors. So now I'm asking, okay, what is a perpendicular bisector? Now I'm hoping this will be the easiest of the words to define, because if you understand the two parts of it, it kind of tells you what it is. What does perpendicular mean? Just blurt it out. Some about 90 degrees. I see hand motions like this. Somebody said right angle. Use your own words. You don't have to copy me. But half of the definition has to say something about it forms a right angle. Okay? So I'm just going to put forms a right angle, or you could have said 90 degrees. And, okay, so that's the perpendicular part. What does bisector mean? To cut in half. And cuts a side in half. All right, using your own words, if you wanted to say something about a midpoint, passes through a midpoint, you could have said 90 degrees instead of right angle. You can use your own words. But that's what I want you to do, is say what is a perpendicular bisector. Then as far as the picture, again, it's all linked together. What I really am looking for you to do is draw me a picture of a perpendicular bisector. So we have a perpendicular bisector. Now you told me what it means. Now show me what it looks like, or show yourself. Really, I mean, these are your notes. Show yourself what it looks like. Well, we just said it. It has to form a right angle. It has to cut a side in half. So here, I'm going to put a dot down here at the bottom, sort of trying to get a feel for where the middle is. Please include markings that show everything. So if this is supposed to be the middle, then maybe I'll mark it like this to show that it's congruent on either side. And now I will try to draw a line as best I can perpendicular to that.
Can you do like from another side?
Oh yeah, you can do any side you want. It doesn't matter. Okay? How do we usually show that things are 90 degrees in a picture? You put a little box, so make sure you put the little box. So show your markings. Put the box, put the little double lines. This is a perpendicular bisector. Notice, does the perpendicular bisector have to hit a vertex? Clearly not. Okay? It has to be perpendicular and it has to be middle. It's the one line of all of these four that doesn't have to touch a vertex. All of the other ones touch a vertex except for this one doesn't have to. So that's what I want you to do when you see that. What do I want you to do when I ask you for special properties? I think you know this already. Right. For this one, you're going to say equidistant from the vertices. And I'm going to show you could make a little picture of it too if you want to. But for right now, write this down. Equidistant from the vertices.
Is it 2 words?
Equidistant is one word. I kind of messed it up a little bit. Now, if I were you, I would go ahead and draw a little picture of that one, just to remind yourself what equidistant from the vertices means in a picture. So this is what I mean. Just make yourself a little diagram, something like this. And there's my circumcenter, and here's what equidistant to the vertices looks like. Okay? That's what I'm looking for you to do. All right. So one more thing. Let's go back and talk about what I mean by in, out, and on. There's an app in here somewhere. Oh, it's not on this one. All right, this is an active image of Circumcenter, okay? You know that at a glance because these are all perpendicular bisectors. So that's how you know, even without me telling you, that this is the Circumcenter. Now, I wanted to show you this because I can move this around on the computer, and even as I move it, you see that pink dot in the middle?
It says that.
Wherever I move it, that pink dot is still the circumcenter, okay? Now, it turns out, depending on how I move this, sometimes that dot will stay inside of the triangle. But watch what happens. As I move smaller and smaller, closer and closer, see how that dot is getting closer to the edge? And then right about there somewhere, bam, it's right on the edge. And if I kept going, it turns out that the circumcenter could actually be outside of the triangle itself. Weird. That doesn't happen for all of them, but for some of these triangle centers can be outside of the triangle. Now, here's what controls it. If I were to say, if I were going to say, here's an acute triangle, here's an obtuse triangle, and here's a right triangle, would you know what I was talking about?
Yeah.
Raise your hand if you know what an obtuse triangle is. Okay, put your hands down. Let the record reflect. Most of the class knew what it was. Okay. What is an obtuse triangle? Anybody? Go.
It's a triangle or an angle that's bigger than 90 degrees.
Right, it's a triangle that has an angle that's bigger than 90 degrees. Okay? So, what kind of triangle are we looking at right now? Is this a right triangle, an acute triangle, or an obtuse triangle? This is an acute triangle right now. So as long as this is an acute triangle, the circumcenter, get off. The circumcenter is inside the triangle. If I, stop it. If I move this to be an obtuse triangle now, there she goes, Maria. You alright, sweetie? I knocked her out. I'm sorry. So sorry. If I push this to be an obtuse triangle, blam, now it's outside of the triangle. What do you think happens if I make it a perfect 90-degree triangle? Let's see. I'm going to drag this down, trying to make it be, well, I guess I better, let's see. Let me play with it. Let me try to make it look like a right triangle like you're used to. Okay? If I make this a perfect right triangle with angle B as a 90-degree angle, look where the circumcenter wound up, right on the hypotenuse. So, just to review, when it was an acute triangle, it was inside. When it was an obtuse triangle, it was outside. And when it was a 90-degree right triangle, it was right on the hypotenuse. That's what I meant by these dots. Okay? So this is a diagram to remind you as you're studying that whenever it's an acute triangle, it's going to be on the inside. So I put a dot on the inside. Whenever it's an obtuse triangle, like I'm showing here, the dot will be on the outside. The circumcenter is on the outside. And whenever it's a right triangle, the circumcenter will be right on the hypotenuse. That's what the dots mean. Okay? Now, glance across all of the dots that I have showing. Look at all the acute triangles. Acute triangle, acute triangle, acute triangle, acute triangle. Do you see a pattern for the acute triangles? They are all inside the triangle. So that's one thing that you can cover right there. If it's an acute triangle, it's always on the inside. So you really only have to worry about obtuse triangles and right triangles. Okay? All right. Go ahead and copy down all the dots. That's the one thing you probably want to just copy right now. Can you see them well enough from where you are?
You stretch them out. Just big.
It's on Edmodo. I can't really make it much bigger. See yourselves the post that you made. So if you guys come to the website and click on this link, it will take you to this website, Quizlet. And there's flashcards there for you. I like to put it on shuffle mode. So, like for example, right here it's asking you what is an altitude. And if you click on it, alright, it's probably too small for you to see. Quizlet. Alright, you probably can't see from where you are, but at your computer you'll be able to see it really well. It says it starts at the vertex and the other end is perpendicular to its side. So you're quizzing yourself with these flashcards. Okay? Angle bisector. What's an angle bisector? Well, that divides an angle into two congruent angles. What's the definition of a circumcenter? In other words, what are the lines that are intersecting for a circumcenter? Intersection of perpendicular bisectors. What's a median? A median goes from where to where? Starts at a vertex, ends at a midpoint. Okay? So these flashcards are there for you. Please go to Edmodo, use the flashcards to practice.